We're going to continue our discussion of continuous probability and how you can calculate it using area under a curve. In particular, we're going to be looking at the normal distribution. Previously, we revisited the idea of a uniform distribution, which gave us a nice rectangle whenever we were looking at area. Now what we're going to talk about is what's called the normal curve or the bell-shaped curve. All semester we've been talking about what we meant by a bell-shaped curve. Well, now we're going to give that a formal meaning. And it's a curve where it's symmetric and the mean and median are approximately equal to each other. And if I were to draw a histogram, the curve that would fit it would have this nice bell shape to it. We talked about it previously in chapter 3 that if we had a bell-shaped curve, we had something called the empirical rule. And it talked about how much of the data would lie within a certain number of standard deviations from the mean. Well, we're going to use a little bit different notation in this one, but it's going to be relating back to what we did previously. And we're going to talk about the variable being normally distributed if it has a normal probability distribution. And they have the shape will then be bell-shaped. It will be symmetric about its mean. And this inflection point means it kind of changes from cupping up to cupping down at this point. But the overall thing that we want you to get is you will have a picture that looks something like this. So here's some examples with the mean and standard deviation at different values. These two things have the same standard deviation and they have different means. So they are exactly the same shape. The only difference is where the center of them is located. Now again, remember standard deviation, which is for population, is denoted by sigma, and the mean for the population, which is denoted by mu, are the two parameters that we have when we're looking with the population. And standard deviation gives me a measure of how far away from the mean are each of my data points located. So that gives us a step size. So the mean tells us where we're going to look at the center of our picture. The standard deviation gives me a step size to put a context on my number line then of how far out do I travel on each side. So notice with the same standard deviation and different means, the only difference between these two pictures is where the center is located. However, if we looked at the second one here, excuse me, if we look at this other example, they both have a mean of 0, so they're both centered around 0, but they have different step sizes. This one has a standard deviation of 1, and this one has a standard deviation of 2. So the one with a standard deviation of 1 is a skinnier curve than the one with a standard deviation of 2. Okay. What we're trying to illustrate by this is that the mean affects where the center of that graph is going to be. The standard deviation will affect the shape of the graph. How wide will it be, or how skinny will it be, and how tall will it be? So let's look at some properties of the normal curve that we could kind of gain from those pictures. One, it's symmetric about its mean. So the mean will be right in the middle of the picture. The mean, the median, and the mode are all the same thing for a normal curve. So it has a single peak, and the highest point occurs at the mean. It has inflection points at mu minus sigma and mu plus sigma. Again, that's more of a shape situation where it's kind of changing the way that it's cupping based off of where these 2 points lie. And it should have been mu minus sigma and mu plus sigma here. So this should have been a plus sigma. Because it is a probability distribution, we do have that the area under the curve is equal to 1. And because it's symmetric, I know that the area to the left of the mean is equal to the area of the right to the right of the mean, and they're both equal to a half. Remember, it's symmetric about its mean. So this mean splits the picture in half because the total area is 1. If I were to drop a line at the mean, half of it, the area would lie to the left and half of the area would lie to the right. The other is that as x gets larger and larger and larger, the graph approaches but never reaches the horizontal axis. And as x decreases without bound, in other words, it gets more and more negative, it again approaches but never reaches the horizontal axis. All that means is the further we get away from the mean, the smaller the probability is, and it gets to 0. But we know that the answer is never going to be negative because we can't have a negative probability. And with the normal curve, we do end up with the empirical rule. Approximately is the key word here. Approximately 68% will lie within 1 standard deviation, approximately 95% lies within 2, and 99.7% lies within 3 standard deviations. It is approximate because under a true normal curve, it's actually a little bit more than 68, and for 1 standard deviation, and it's a little under 95% for 2 standard deviations. So these are approximations. And again, this is the picture that we saw earlier when we were talking about the empirical rule. So if we had this bell-shaped curve, that's about how it would break out. The normal distribution is used for a variety of applications. What we're going to learn as we move through the rest of this course is that the normal distribution pops up in some unexpected ways. For example, let's look at the next slide where we have the heights representing a random sample of 52-year-old males. 52-year-old males. Okay, so there are 50 people in the sample and there are 2-year-olds. So we're going to draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. If we do that, we notice we do get something that is somewhat bell-shaped. It's not going to be an exact fit when we're putting a histogram on there, but it does have, it does look pretty symmetric about this middle part here. And we can draw a normal curve over the top of it to see that it does fit pretty well. And if we're wanting to try to approximate the percent of the population that would be within a certain range, we can look at area under this curve to help me out. So rather than looking at the actual histogram, I can now start looking at the area under this red curve to try to give me an estimate of what percent of 2-year-old males would be at a specific height or in a height range. So suppose that we're looking at area under a curve and we're told that the variable we're looking at is normal, has mean, mu, and standard deviation, and the area under the normal curve then represents the values the area under the curve for the interval of values of the random variable represents either sorry, it took me down way too many I have no idea why it took me all the way to the end of that section. Okay, here we go. Now we're back. We can look at it as two ways. The area under the curve is the proportion of the population with a characteristic described by the interval of values, or it's the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. For example, let's say the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200. And it has us go through some processes here. First, it wants us to draw the normal curve. Then it wants us to shade the value under 2,100 pounds. And it says, suppose that the area under the curve 2,100 is equal to 0.3085. Interpret the result. Well, for drawing it, remember the mean is the middle of the picture. The standard deviation is my step size, so I'm going to go out by a couple hundred each time. And they went out by 100 here to help with the next problem that we're going to do. But we get this nice bell-shaped curve, and the mean is in the middle of it. Now, if we put on 2,100 and we shade to the left, this would be representing being a weight of 2,100 pounds or less. So if I know that this area is 0.3085, what that tells me then is that there are two interpretations. 30.85% of all giraffes will weigh less than 2,100 pounds. Or equivalently, if I grab a giraffe at random and I take their weight, the probability that that giraffe weighs less than 2,100 pounds is 30.85%, or 0.3085. So I can either say it's this percent of the entire population will have this characteristic, or if I select one out of random out of the population, it's the probability that that one selected will have the particular characteristic. So in the next section, we're going to begin talking about how do we take these measurements and calculate this area more accurately than what we can with the empirical rule. So this finishes up this particular section.